Okay. We're going to discuss sections 10.7 and 10.8 this week and take our quiz next week, and then we'll come back to 10.6. Okay. So today we're going to talk about polar coordinates. And before I just tell you how to do it, I want us to really think about things. Okay. Because how we work with polar coordinates relates a lot to what we did maybe at the beginning of the semester. Okay. So rectangular coordinates are what you are used to. Okay. Where you have an X and Y axis, you have an X and Y coordinate, and you move in a rectangle. Okay, that's why they're called rectangular coordinates. You're going to move right or left. Hold on, this is perfect. Okay, you're going to move right or left X, and then up or down Y. So you're moving in a rectangle, right? So, and then we get to a coordinate. Okay, we move rectangularly. Okay. Now, when we talk about polar coordinates, okay, technically we could still use the X and Y axis, but we are going to use angles instead of right and left. Okay. So a polar coordinate, okay, notice how we have concentric circles. Okay. So R is how far we move out from the origin, kind of like a radius. And theta is how far we rotate from the polar axis. Okay. So theta is an angle. We've graphed those before. And R is how far we move out from the origin. Okay. I would write that down. And just like with everything else that we've done, we keep that alphabetical order, X, comma, Y, right? We had cosine, comma, sine, right? See the next. R, comma, theta. The R comes with the T, okay, alphabetically. Now we're going to work a lot more with how we do this, but just before we get into kind of our hey, let's think about things. This coordinate right here is lying on the angle 3 pi over 4. Do you see that? Okay, so we rotated 3 pi over 4 to get there. And then if we count these little circles, 1, 2, 3, 4, we're 4 away from the origin. So this coordinate we would call 4, 3 pi over 4. We're gonna do something right now, and you and your pod are gonna have to talk about things and kind of work together. Okay. Let's think about the coordinate 2, 2. Describe to me how to graph that. Rectangular coordinate 2, 2. I'm going to go right 2 and then up 2. That's my coordinate. Okay. I went right 2 and then I went up 2. Okay. Now this is what I want you to do. Given what we just talked about with polar, how would you describe this using the polar way? In order to get to this blue dot, how far would we have to rotate? How far would you need to travel out from the origin? And how would you write it? I'm going to give you about 2 minutes for you and your pod to talk about what you think needs to happen in order to get to that coordinate by rotating an angle and then walking out to that coordinate. Okay? Talk about it. Talk about it. disagree.
It looks more like 60 because it's in between.
I like the pi over 4, but I don't like the R.
Well, if you did,
What? What's a right triangle?
largely. What about thoughts on that?
Radical 8 sort of makes me cringe.
Oh, yeah.
Should we maybe fix that a little bit?
Two radicals, like,
I like that a lot.
it's like the affluence. Oh, it's this.
Yeah.
Or just see that.
Radical 8.
You just.
All right, so let me do this to our picture. What do we have? A right triangle. Okay, this angle right here, how far do we have to rotate? I heard 45 degrees. And then how far from the origin do we have to walk out on this hypotenuse? 2 radical 2. All right. So our coordinate is 2 radical 2 pi over 4. That's our polar coordinate. Now, how did you get the pi over 4? Question. You just looked at it and you just knew it would be that? How could you if it wasn't 2 and 2? 4. What if they're not unit circle values? What if they're 1 and 7? No? You know the answer to this question. If I'm trying to find this angle right here and I have this adjacent side and this opposite side, we could use yeah, tangent. Tangent would help us out a lot. Okay, so let's talk about this coordinate right here, -3, 4. How would I plot that? We would go left 3 and up 4. Go left 3 and we would go up 4. Okay, same thing. I want you and your pod to figure out how far we would rotate and then walk out from the origin to get to that coordinate. How far would you have to rotate and then walk out to get to that coordinate? I'll give you a couple minutes. You might need a calculator. I've never been there, but I feel like I could spend a lot of money if I did go there. Which is maybe why I have. Yeah, 53 degrees.
Yeah. So
Do it, not at night.
Word way looks good. You get this.
Do you have this figured out?
Yeah. Four over 3, right?
No. We always go back to the x-axis. So it's either 180 or 360 all the time. All right, let's talk about how far we would have to rotate. Isaac, how far would we have to rotate to get there? Can you talk me through how you got that? Okay, so you took the inverse tangent to get your reference angle, but then we need 180 minus that 53 degrees. Okay, so we have 126.9 degrees. How far would we have to go from the origin out to the coordinate on that red hypotenuse? How far is that? Probably about 5. So we would write this coordinate as 5, comma, 126.9 degrees. Okay. Now, that is the last time you are going to use your calculator this week. I'm going to take it back. That is the last time you're going to use your calculator in order to do a problem this week. Tomorrow you will need your calculator because you're going to like play around with graphs. But everything that we do with polar coordinates is going to be without a calculator. So we're going to keep in radians and we're going to keep to our unit circle angles. Okay, so unit circles coming back for us, which is good. Okay, it keeps it fresh. All right, you're not going to forget it. So let's, now that we've kind of played around with some coordinates, let's actually talk about what our conversions are going to be to go from a rectangular to a polar or a polar to a rectangular coordinate. So I'm going to draw an XY axis here. I'm gonna draw. Okay, I'm gonna draw an XY axis. That was a terrible one. In blue, I have that we're gonna go right or left X, and then we're gonna go up or down Y to get to our coordinate. All right. Now, in red, we are going to rotate theta and move out R. So let's talk about some relationships here. Okay. What did you use in order to get the hypotenuse? The Pythagorean theorem. We know that x squared plus y squared equals r squared. You gotta write that down. What other strategy did you use when we were trying to figure out theta? We knew x and y, and we were trying to find theta. What did we use? Huh? Tangent? The tangent of theta is y over x. Okay. Don't write this down quite yet. But we also know that the cosine of theta is adjacent over hypotenuse. Do you agree? So if I multiply that r over to the other side, x is r cosine theta. That looks kind of familiar, doesn't it? This one you can write down. Flashback to vectors a little bit and how we worked with that picture. We're gonna do the same thing. We know that the sine of theta is y over r. And so if we want if we want y by itself, we can multiply r to the other side. Y is r sine of theta. These four are the equations you are going to use to convert anything from either rectangular to polar or polar to rectangular. We are going to work on converting polar coordinates to rectangular and vice versa. We're also going to work on equations and converting them back and forth. we do get to graph this chapter, and it's gonna be a lot of fun. It's gonna be a lot of fun. Okay, now, are any of these equations, do they look brand new to you? We've worked with all of these before, okay? We're just working with them in a different context, okay? So today, we're gonna just practice using them. We're gonna practice getting used to how to plot polar coordinates, how to name polar coordinates, how to convert polar coordinates, okay? All right. We are going to plot the coordinate 3, comma, -3 pi over 4. Now, the good news for you is that this is your only book assignment for the week. Everything else is worksheets, okay? But if you want to draw it in your notebook for this example, you can make like the X and Y axis. And then if you want to make like the 45-degree angles, and then you can make some concentric circles. What? Concentric circles? I did not. Circles who have the same center, concentric circles. They share a center. You talked about them before in geometry. Yeah, that's true. All right, so I know that we are getting our coordinates as r comma theta. I understand that. However, I think that to plot these coordinates and to think about these coordinates, it's easier to think about the angle and then worry about how far we are from the origin, okay? So if we're gonna rotate -3 pi over 4, what quadrant does that put us in? That puts us in the third quadrant. -3 pi over 4 would be right here along this angle right here, okay? So this right here is our -3 pi over 4, okay? So once we rotate there, we're gonna move out 1, 2, 3 on our concentric circles. There is our coordinate right there. Now, if we keep our angles between -2 pi and +2 pi, there are 4 ways to name an angle or a coordinate. Okay, so here's one way, 3, -3 pi over 4, but there's 3 other ways that we can name it. Okay, instead of calling that angle -3 pi over 4, what would be the positive angle that we could rotate to get there? Okay, so we could call this 3, 5 pi over 4. Okay. Now, going back to what we first wrote down, r is a directed distance from the origin. Directed distance. That means r could be positive or r could be negative. If r is negative, that means we're moving backwards. So bear with me here. If we rotate to pi over 4, we would move backwards 3 from our pi over 4 angle to get here. Do you see what I'm saying there? So we could call this -3 pi over 4 because we could rotate the pi over 4. Instead of moving forward, we move backwards 3. Now, pi over 4, what if I called that a negative angle? What negative angle would that be? Starting here and moving negative all the way to the first quadrant. Okay, we could call that angle -7 pi/4, and we can move backwards to get there. You can, I'm just telling you, there's always going to be multiple ways to name your coordinate. Okay, and it's something I'm gonna ask you to do. I promise you that on the quiz on Tuesday, I'm gonna ask you to take a coordinate and give me 2 other ways to name it. There's gonna be 3, but I'll even just ask you for 2 other ways. Okay, are you okay with why it's negative? That's no, okay. So I'm going to a different angle. I'm going to my first quadrant. And instead of moving forward on that angle, I'm moving backwards to the 3rd quadrant. So my direction is negative because R is a directed distance. Okay. My suggestion to you is that you're probably going to have to plot more than one coordinate. So draw this cute little picture with all of, so I have like the pi/3, pi/4, and pi/6 angles. And then anything you have to plot them all on one. So if you have to plot 5 points, draw this once and just plot your 5 points on here. All right, let's go ahead and converge. I want to convert -1 to polar. So I have a rectangular coordinate that we want to convert to a polar coordinate. You don't have to actually plot it, but you have to think about what quadrant it is in. Which quadrant is -1, 1 in? It's in the 2nd quadrant. Okay. So whatever my final answer is, that should also match being in quadrant 2. All right. So we need R and we need theta. Okay. Well, when we have a rectangular coordinate, we know X and Y. What 2 equations involve both X and Y? These 2 right here. These are going to be the 2 that are going to be the most beneficial to us. If we know X and Y, we can get R. If we know X and Y, we can get theta. All right. So let's use our Pythagorean theorem. We know that X squared plus Y squared equals R squared. So R squared is 2, which means R is technically, yes, plus or minus radical 2, but we're going to choose the positive R to write our coordinate just to keep things simple. Okay. Well, now we need to figure out theta. The tangent of theta equals y/x. So we have the tangent of theta equals -1. Now, number 1, we're not using our calculator. Number 2, there's 2 different places on the unit circle where this happens. We have to make sure that we choose the correct one. So since we're in the 2nd quadrant and the tangent is -1, what does that mean our angle is? What's our angle, Patton? Pi/4. Yes. I am always going to go straight to a positive R and a positive theta when I'm converting. Okay. So if you're ever like checking answers in the back of the book, checking answers with mine, they're going to give you the simplest coordinate to get to. Okay. Don't you feel like this is math that we've done before? I mean, these 4 equations, aren't they very similar to things that we did with our vectors? Right? right. All right, now I have a coordinate that is in polar form that I want to convert to rectangular form. So write it down. Okay, now this time x squared plus y squared equals r squared is not going to help us because we need x and y. All right, so we need the two equations that have both r and theta, since we have both r and theta, and then that way we can solve for it. Okay, so we know that x equals r cosine theta and y equals r sine theta. The cosine of pi over 6. Kristen, what is it? Yeah, radical 3 over 2. So the cosine of pi over 6 is radical 3 over 2 times radical 3 would give us 3/2. Y equals radical 3 sine of pi over 6. Well, the sine of pi over 6 would then be 1/2 times radical 3. There's our coordinate. Does it make sense that we have a first quadrant coordinate for our answer? Yeah, our angle is pi over 6 and we have a positive r value, so that makes sense. Okay. This conversion you have to think less about because the trig is going to take care of whether you should have a positive or a negative answer. You just have to remember where you have positive versus negative sines and cosines. Okay. All right, now we are going to convert equations. Okay, when you are converting equations, I need you to substitute your conversion formula. So if you have x's and y's and you want r's and thetas, use whatever formula is going to help you get there. Okay, we like to solve for y when we have rectangular equations. When we have polar equations, we'll like to solve for r. Okay. Now, this is something that you are going to have to process each one a little bit differently. Okay. You need to think about what you have and how to change what you have into the other kind. So if you have r's and thetas, how do we get them to x's and y's, or vice versa? Okay. There are a couple types of problems that you'll see over and over. There's some that are way more simple than others. But my suggestion, especially while you're going through your homework tonight, and then next week when you're reviewing, having these 4 conversions written at the top of your paper for reference would be a good idea. So how about I write them on the board so we have them right in front of our face? There we go. All right, first, R equals 2. We're going to convert that to rectangular. It is a polar equation. R equals 2. I don't know what to do. Let's think about what the picture would look like. If R is always 2, the distance from the origin is always 2. What does that look like? It's a circle with radius 2. Okay, so this is what we can do. Are we allowed to square both sides of an equation? So now I have R squared equals 4. Do we know what R squared is the same as? Which is totally a circle with radius 2. There we go. Good. So it looks like circle with radius 2. All right. Theta equals pi over 3. If theta is always pi over 3, what does that look like? The angle is always pi over 3, no matter what R is. What does that look like? The line where theta is always pi over 3. Okay, so let's talk about how to get it into X's and Y's. Well, I have 3 equations that involve theta. Well, I don't want theta anymore, and I don't want R anymore. I want X's and Y's. So I have one equation that involves a theta and an X and a Y. But it's tangent of theta equals Y over X. Could I say that the tangent of theta equals the tangent of pi over 3? Could I do that? Is that allowed? Yeah. If I do something to one side, I do it to the other side, we're fine. Well, what's the tangent of theta the same as? Same as Y over X. Okay. And what's the tangent of pi over 3? I know it. But do you know it? Radical 3. So Y equals radical 3x. Now, if I were to graph this line, I think I would much rather have the equation theta equals pi over 3 and just make a line at pi over 3, as opposed to have a slope of up radical 3 over 1, up radical 3 over 1. I feel like that wouldn't be quite as accurate. Okay. Sometimes our polar equations are better to work with than our rectangular. Sometimes it's the other way around. Last one from polar to rectangular, and then we'll switch. Right again. Cosecant. Do we have anything about a cosecant in any of these 4 conversion formulas? No, we have sine, cosine, and tangent. Cosecant is not helpful at all. So let's rewrite cosecant to be the reciprocal of sine. Interesting. What can we do? What if r and sine of theta were together? Could we like make a substitution? Yeah. So if we multiply the sine of theta over to be with the r, we now have y equals 4. Pretty slick, right? Something very exciting is happening over there. I wish. We got to finish a couple examples. Okay, so now we're going to go the other way. All right, we're going to go from rectangular to polar, and that's how we're going to finish our day. Okay, you're going to do your homework like responsible children. We'll meet back tomorrow. All right, x equals 3. Now I like going from rectangular to polar because it's a little bit more straightforward. X is our cosine theta. Y is our sine theta. So if I have x equals 3, well, I know x is our cosine theta. And if possible, when you have a polar equation, I want you to solve for r. Now, sometimes you can't, and that's fine, but if you can, I would like you to. So let's go ahead and divide over the cosine. Now, if you write it like this, I don't have a problem with that, but you're going to see me write it as 3 secant theta. Very similar to that last question that we had going from polar to rectangular. Make your substitutions, solve for r if you can. Put a smile on your face. I like this example. Write it down. Now, typically, I would say substitute r cosine theta for x and r sine theta for y. But if there's something that is a lot more simple to substitute, go for it. What do you see? X squared plus y squared. Do we have a substitution for that? We totally do. And you could do r cosine theta and r sine theta and get to the same place, but we know that x squared plus y squared is r squared. So we can write that we have the circle r equals 4 in polar form, and we're fine. All right, can we call that a day? We can call that a day.